Good morning or good afternoon, depending on where you are. My name is Derek Pizarro. I'm a senior manager with AST Environmental, and this is the fourth installment of RPI Group's winter seminar series. This is Working Smarter, Not Harder to Characterize Fractured Bedrock. For those in attendance, I'd like them to think of this as a two-part series. This is the first of two. Next week, we're going to be talking about the injection. This week, we're going to be talking about the characterization of bedrock and how we move into an injection phase at your site. So first off, thank you for joining us. I know many of us are busy, especially at the end of the year and with everything going on. But I did want to say thank you to you, the attendee, and also a big thank you to Remediation Products, Inc., RPI, for hosting these. We did these in the spring, slightly different presentations. If you joined us for the Bedrock one in the past spring, it was a 1-unit series. This is broken up into 2, so this is a much deeper dive than you received in the past. So if you or colleagues would like to review a summary, those videos are available on RPI's website. But I hope you join us today and next week for a comprehensive review of how to characterize and treat bedrock contamination at your sites. I think most of us are pretty familiar with GoToWebinar, Zoom, etc. these days. So if you have a question asked, there's a question and a chat, and we'll be monitoring those. We'll field those questions at the end of the presentation. Again, here's just a brief look at what's remaining in the winter webinar series. We're number 4. Number 6 is part of this as well. The pre-drill methodology we typically use for weathered bedrock transition zone applications. So this still ties into what we're dealing with here this week and next. A lot of sites we do find we have to treat the transition or weathered unit as we approach the competent rock below. So it is, if you join us for all 3 of these, it will be a very comprehensive approach at a bedrock site where most of us might encounter. So a real quick look at RPI Group and AST and our installer network. This is really the tripod, the foundation of what we're talking about here today, what we're built on. RPI is the technology developer for BOSS 100, BOSS 200, CAT 100. They also run our project support laboratory. We'll share a slide about that later on in this presentation. As for AST Environmental, we operate a bedrock injection truck, a remedial design characterization system, which we'll talk about today specifically. And then we also have other installers in this group. Typically, if we're doing a bedrock site, you're working with all 3 units here, specifically RPI and AST, and possibly a local installer being involved as well. And in terms of footprint, we're pretty well distributed throughout the US and international as well. In terms of bedrock, though, you're typically looking at operated in North America when it comes to the bedrock truck injection because we're limited by where we can move that. So how effective is this RDC and injection approach we're talking about this week and next? Well, this isn't a total list, but it is just a brief look at a history of how successful this RDC and injection system is coupled up together here. These sites here in red, a mix of CVOC and petroleum projects. These are projects that have an NFA. You could see early on, just due to the proximity to our headquarters in Kentucky, we're doing a lot of local work there in that region. But as you see, as we move into sites where we've done pilots or we've done full scale and then monitoring, they start to stretch out across the country. We were very fortunate this past summer to do a demonstration project at a military site in California. We're very excited about those results. So this system, will travel, I guess is the best way to put it. And there's also different pieces we're going to talk about here today that can be utilized either through one of our other installers if it's not AST, or it's other preferential companies you like to work with up front. We can take that data and transpose it into the RDC and thus injection phase. So here's today's roadmap. We're going to talk very briefly about the CSM, and then we're really going to spend a lot of time on the RDC component here. And then my colleague Bill Brab, who's going to co-present with me here today, he's going to take you through a case study and an updated CSM as well using these techniques. So let's start with the bedrock RDC because that's the bulk of what we're dealing with here today. For those of you who haven't done an RDC with us before in overburden, it's a very similar approach to what we're doing there, except our tools are very different. The distribution between cost of RDC and injection cost, the distribution's a bit different between an overburden and a bedrock injection. But the biggest thing to note is we're still following a process of reviewing information that's available to us at the outset. We're looking for data gaps. We're looking for uncharacterized areas, mischaracterized areas. And then we're going to walk through that RDC process, today's presentation. And what this will allow us to do is come up with either a redesign, an augmented design, adapting or expanding an existing design. And that takes us into the implementation, which next week's presentation will focus on. So at the outset, we're looking at what data you have available. One of the things we always tend to find are constructed, cased, screened wells, long well screens. We like to call this existing infrastructure. Unfortunately, those existing wells within that infrastructure are typically under-characterizing or provide limited characterization to what we need to accomplish in an RDC. And that's mainly because of these long open intervals where various fractures, secondary porosities are all mixing in this very long well column. It's actually diluting the overall picture, or it's placing zones of contamination that may not truly exist in terms of a fracture or secondary porosity. So you don't get definition between your intervals with a lot of sites where they've done bedrock characterization in the past, because at some point someone's selectively chosen casing and screen intervals or open borehole intervals based upon what they think they know about the site at that time. Whether they use geophysics or not is a whole nother discussion. So it can be very hard to use existing infrastructure at a site. The other thing we don't usually see in a CSM is we don't know rock mass. A lot of CSMs include data which was done by air rotary traditionally, and we looked at rock chips coming up, expelled during that process. Rock chips are nice for kind of characterizing the geology we're in, but we really need rock cores. We need to look at where the mass is residing within the rock matrix, and we need to define intervals, specific geologic zones. And then that all needs to be coupled up with a borehole geophysics program. That's going to show us where groundwater zones are within, whether they're receiving zones, what type of fractures we have. Are we changing lithologies here? Are we changing fracture networks if we're moving between different units? Are these limestones, shales? If we're moving into harder rock, we really need to have a good resolution on how we come up with the design. So a lot of times the CSM doesn't have that, and a lot of that is limited based upon available budgetary cost up front or historic limited investigations. I'd say a lot of bedrock sites that we see typically at this juncture have data that stretches back into the 90s, and a lot of that data isn't terribly useful either to the design that they used at that point in time, the equipment they used, the monitoring equipment for the wells, how they drilled them, etc. So we really need to modernize that and update it. So one of the first things we do is if we decide to augment the existing well network at a site, something, if we have the ability to do, adds some great resolution and improves the chances of selecting an area of the site where we can install a well that will be productive for injection. One of the easiest ways to do that is to use geophysics, specifically electrical resistivity and induced potential, and then coupling those up with seismic. Again, each of these provides a different component. Combined, they give us good resolution at the site. And this allows us to hopefully select a much better or higher probability location where we're going to have fractures, features, secondary porosities where injection is going to be advantageous to remediating your site. The pictures here, if we want to take a quick dive on these, the upper picture here is electrical resistivity, and the sister picture there's the induced potential. Think of resistivity as energizing the whole system, and then induced potential as the bleed off, the dissipation of that energy. So those two couple up very well together. And then the bottom left there, this is a seismic profile, multi-channel surface wave analysis of a site, same site. And you can see how combining these different geophysical tools will allow us to look at areas where we may want to target denser rock, or if we're doing transition zone where we need to know that softer or weathered unit is that we need to drill into to actually treat this contamination, this contaminant's concern in that interval. I'll turn my pointer on here, excuse me. There we go. Okay, so go ahead.
Yeah, go ahead. That's making sure my audio is on for the transition.
Okay. Yeah, I think we had a little hiccup there. Sorry about that, everybody. So the other thing to consider too is now we've selected areas based upon our CSM or our geophysics that we want to possibly install an additional well. Again, when it comes to the injection, we need open, uncased, unscreened boreholes to use these packer and characterization setups for both discrete sampling and geophysics. So some preferences for installing these wells typically are personal to your geologist or engineer. In the part of the country that I typically operate in, we find a lot of air rotary installs. So I'm obviously deferential to that technology. Definitely makes a nice clean borehole you can easily blow out. But other places, people are using sonic, whether it's for coring or installation as well, and that works just fine. I know Bill has some experience with that, which he can talk to as well. But for me, getting a nice clean air rotary hole that's available to me for geophysical characterization is extremely important. And the last thing we're going to talk about, regardless of who you're using to install these wells, please be very careful about the bit that's being used. We don't want heavily worn bits. We need a nominal 6-inch size. That's the ideal diameter for a borehole or well for us to get geophysical tooling and thus an injection system down. So think of a 6-inch nominal size as Goldilocks. I know a lot of drillers here in my area start out with maybe a 6 and an 1/8 inch bit, and they run them down to 6 inches, and then they move on to a new bit. But I know some drillers don't always do that, and the size for that bit can eclipse sub 6, and then that becomes a problem for getting tooling downhole.
Yeah, I'd agree with that definitely, Derek. That's a good comment as well, and we've noticed with the sonic bits as well that some of the upper limits of the sonic bit tooling on the borehole tends to be on the higher side. So just having that communication on the front end with your drilling contractor and all the parties involved is quite important to make sure that as we approach investigation and ultimately remediation, we're filling in all the blanks and making sure all these components are ideal for future considerations that may be utilized on a site. So transitioning into what I want to talk about as importance for drilling considerations as well is getting into this character of the geology itself. As Derek had mentioned before, typically, consolidated geology monitoring investigation points are installed with air rotary methods or methods that essentially the end process is simply just to get a cased well in. But like he said, looking at rock chips coming from an air rotary hole, for instance, does give some indication of just general geology, but doesn't really tell us a whole lot of information about the actual nature and orientation of the geology itself. And so it's quite crucial as part of any sort of remediation investigation plan to include with your geophysics some sort of coring schedule and actually having those cores available to interrogate the borehole prior to doing any geophysics or any follow-up investigation work on those. And I like to think of this in context of looking at, an overburden type scenario, running a dual tube liner down prior to advancing your hollow stem augers. And having that core, that dual tube liner in front of you allows you to look at the structure, texture, and variation of the lithology in log form, being able to look at it in front of you on the table rather than a composite blob of stuff coming out in a pile. Obviously, you can look, touch, hold, and do any type of sampling of that material. There is methodology for being able to take matrix samples of the rock itself. You can have that in front of you for scrutinizing when you're looking at your two-dimensional wireline logs or looking at it with your downhole camera. and being able to do some sort of forensics on the chemistry of some of the anthropogenic effects on that matrix material itself. And so, for the purposes of our characterization and ultimately remediation, the methodology or the type of construction that we would like to have for the wells within the consolidated geology is to have surface cased open borehole wells. And the benefit of these is that you can use them for an extended number of characterization tools, but then ultimately they can be used for the remediation of the geology itself and the groundwater by use for our purposes for injection wells. And so these are multi-purpose access features. They're not just drilled into the geology for the purpose of looking at diluted, dissolved chemistry for monitoring purposes only. And back one slide, please, Derek. And so just looking at the pictures on the right-hand side, looking at the tilted beds of limestone here, the far right picture has in the second core, looking from left to right, kind of this feature that I'm holding propped up here. And essentially this interval here, I like this because when looking at this here, you could clearly see precipitate and weathering of this particular interval, showing that we have a potential groundwater transport zone that we really want to look at closer when we come back into this borehole with other tools to assess this. Okay, next slide, please. And so we talk about fractures and features, and essentially looking at these items within the borehole itself, we're looking at typically secondary porosity features. And these are usually identified with what we would see within the caliper logs, like bedding plane separations, joints and faults, lithologic contacts, potential hydraulic zones when we're looking at it with a camera, seeing instances of producing groundwater or receiving groundwater, erosional plays or enlargements from dissolution or whatnot, and then even potentially features that show a weakness in the geology during drilling. And what we want to be also careful of here is when looking at these is some of these features we may want to interrogate a little bit more later on down the line, or some of the other tools that we have that may not look like they're truly groundwater producing, but with developing those particular features, we may be able to find that they actually are key players within the groundwater chemistry that we're seeing within that borehole. And we'll talk more about that and why the injection tooling is critical for success in these particular applications when we go into our webinar next week. Next slide, please. Unless there's anything else you wanted to add, Derek.
No, that's fine. Just had a delay in the system there.
Gotcha. All right, and getting into some of the geophysical logs for the downhole tooling, the downhole investigation that's being done. A lot of these tools are going to probably be familiar to a lot of the folks out here, but we'll want to talk about each one individually here. And so your standard details that kind of come off the shelf, so to speak, with a geophysical study would be your 3-arm caliper. For those that don't know, this is going to be a tool that basically is measuring the aperture or the diameter of the borehole as the tool is advanced from the bottom of the hole to the top, essentially feeling the variation of the bore diameter as the tool's coming out of the ground. Natural gamma, looking at some of that background low-level radiation from the material, resistivity of the aquifer itself, and then looking at the fluid temperature and conductivity. And then some of the additional details that add value to these particular logs is optical televiewer or acoustic televiewer, or looking at E-pulse flow meter. This is beneficial for looking at potential sinks and springs within the borehole itself. Next slide, please. So moving into a brief video clip of our downhole camera in action, moving down the borehole, has the ability to look straight down, but then also turn 90 degrees and rotate, panning from left to right, looking at the full 360-degree view of the borehole. And so taking our core log that we talked about earlier, we can zero in on some of these features. And looking at this particular interval at 59.2 feet below grade, just one of those features I was talking about before that we can see some indication of transport and precipitation within this particular interval. And coming back in with pumping tests as well as actual induced flow, trying to inject material within this interval, tells us that when we actually look at this, this is actually a high producing zone or a large contributor based on contaminant mass and connection with surrounding features across the site. So using this tool again can help us zero in on that specific depth and know how to target that injection plan or that investigation plan appropriately on a borehole by borehole basis. Next slide, please. So getting into the investigation part, one of the custom tools and really unique tools that we utilize within our arsenal for these RDC purposes is the discrete interval, short interval packer that we have within our tool set. And series of photos on the right-hand side will be referenced to supplement the bullets on the left. But looking at the geophysical log, we can see that there's some, based on the caliper, we're seeing some very tightly spaced fracture zones or zones that we would like to scrutinize with a little bit more detail and find out what's occurring within those. And looking at the far right-hand photo on this particular slide, we have the discrete interval packer in side-by-side comparison with a standard traditional off-the-shelf packer that you would utilize that has a much larger sampling interval in between the elements when inflated. And so looking at the measurements here, the larger interval one is somewhere on the order of about 5 feet from packer shoulder to packer shoulder on the upper and lower elements, whereas the discrete interval packer can see in side-by-side comparison is a much narrower interval. And that image is enhanced in the far left photo, showing that we can isolate between the shoulders of those inflated elements 18 inches. And so looking at the caliper log on the left-hand side with those fairly tightly spaced intervals with the larger packer zone, especially on that upper 5 to 12 foot zone, we may not really know which of those specific intervals the producing unit may be coming from. And so with the discrete interval, we can actually isolate those individual fracture features and start to interrogate those particular intervals a little bit more and find out what's going on from those individual intervals. And then finally, to get to the center picture here, we have the brother and sister, so to speak, packers that we utilize for both injection, remediation, and characterization. The one on the left with the yellow shroud on the center will be talked about more next week. The one on the right is the characterization packer. And looking at the bullets here, this straddle packer has a gruntless ready flow tube pump in the bell chamber at the bottom. It also has transducers located within the packer element itself, one above the packer for looking at hydraulic connection or hydraulic characteristics above the packer element, one within the element, and then one below the element looking at vertical connectivity or vertical seal within the borehole itself. And this coupled with transducers in the surrounding formation itself allow us to look at hydraulic characteristics during pumping tests, not only within the borehole itself, but within the surrounding formation closest to the point of pumping from that well. Next slide, please. And why is this discrete interval so important? And so, we kind of talked about earlier the need for having that narrow interval for being able to test and assess specific intervals within a borehole. Busy slide here. I'll try and move through it smoothly and quickly. Left-hand plot, geophysical plot, shows MW10S, which is approximately 10 feet from PW3, which is represented by the two adjacent logs, middle and right. PW3 was the compliance well on site at the time that this project came to our attention, and was still showing elevated concentrations of TCE within the well. And it's fairly deep. We're only showing 2 plots here, but it goes almost 80 foot deep, if I'm not mistaken, on the total depth of this well. Historical studies had utilized just the geophysical logs to try and identify where the contamination is coming from. And so looking at the pointer on the screen here at roughly the 21 to 22 foot interval, a significant high K zone was identified from the geophysics as being a potentially likely candidate for contaminant mass to be moving across the site. And so a previous remediation effort was to inject potassium permanganate, upgrade it from this well, and utilize extraction from this well to pull the permanganate through this high K zone to this particular location. Following that remediation program, like I said, the concentrations did remain elevated within this well, and so looking at some alternative characterization remediation options brought us into the picture here. And so part of the characterization plan was installing MW10S on the left-hand side, but then also coming through and doing this discrete interval testing. And so if we look at the fluid temperature column on each of these 3 plots, what we can see is if we're at that middle column or the middle graph right now that Derek's pointing at, if we're looking at that specific interval, the potassium permanganate did a pretty good job of remediating TCE and getting it down to low-level ppb concentration at that high K zone. But if we move further down the borehole, excuse me, we can see that some of the other producing intervals that were present within that borehole are actually generating some significantly higher concentrations of mass within that particular borehole. And looking back at the far left-hand side, at MW10S, looking at the distribution and effectiveness of that potassium permanganate, again, we're only 10 feet from this particular well, but definitely in the same flow path as where the material is injected and pulled to. We can see that even at that high K zone that's identified in this borehole as well, we still have elevated mass that's present that's an order of magnitude higher than what we're seeing in the well next to it. So the point that we want to make here is that the geophysical tools are a tool, and that they are a part of the whole package of evaluating a site and providing resolution for what's going on in the subsurface. We want to use all of these tools to our advantage to characterize the site. So knowing what we know here is that there are other intervals that are present and need to be addressed as a global assessment and a global treatment for the remediation of this facility, and that we're not just looking at this high K zone that was identified in this previous geophysical study. So next slide, please. And we're just going to look at another example here of why targeting specific intervals is quite important, and having that narrow interval, discrete interval packer is quite important as well. And so this particular site is a petroleum site where if we look at the benzene concentration is fairly uniform. I mean, there's some varying concentrations, but they're all within the same order of magnitude of each other down the borehole. And so even when looking at these discrete intervals, there's nothing strikingly significant about the numbers here. But when we look at looking at the volume pump and what we see coming out of the borehole as we're pumping, again, pulling from these respective intervals as we get to that 42.5 and 43.5 interval, as water was withdrawn and pulled from these particular intervals, naples started coming out of these particular intervals that we were isolating within the borehole. So when coming in with a remediation plan, knowing that the napple is coming out of 2 specific intervals allows us to be a lot more aggressive with the remediation plan within those 2 target intervals, and knowing that they're located there. And so seeing also the spacing between these particular intervals, without having that 18-inch short interval packer, we would not be able to see this kind of resolution and know where that napple is specifically coming from. Having that tool available to us allows us to walk up and down that borehole at tighter intervals if need be to really get some more detail and higher resolution of those particular locations within that borehole and what's going on. Next slide, please. I think this rolls to Derek now.
Yeah, so I'll jump in here real quick. In the interest of time, I'm not going to spend too much on this. We can get into this in the Q&A section. So if you want to ask questions about this, please do so in the questions box there. But I did want to show you some other tools that are out there. Again, a tool is a tool, right? There's different ones you need in your toolbox to solve a site problem. What we're looking at here is on the left side are some very common alternatives to the Packers for RDC that Bill showed you earlier. These can be used in either sentinel wells, or these can be taken in and out of the holes you're going to be used for injection. We see, very popular ones here on the left, flute liners. I have some experience with those, West Bay, Waterloo. We actually use some of these systems in some of our case studies that are available on RPI sites, so you could look at those there. But these have, advantages and disadvantages like every tool. The biggest advantage is these provide depth discrete data, extended time periods to evaluate that same feature, fracture, interval. They can be, depending on the deployment, inexpensive or expensive. Again, a tool is a tool. But the idea is to decrease the amount of boreholes you have on the site, especially if you're reusing these, you're pulling them in, pulling them out during injections or post injections, replacing them. They can be advantageous. Again, disadvantages with every tool, cost could be a factor at your site. These may not make sense for even a large site. They may certainly not make sense for a very small site. And then you talk about O&M, lifespan. All these have different costs, lifespans, maintenance requirements associated with them, but they are versatile. They've also been continuously developed over years. So the initial systems have gotten improved. Their lifespan, even in very heavily impacted environments or even corrosive environments, have gotten a lot better over the years. So these are all tools that can be used to augment things we've talked about here today. And we can cover them more in the Q&A, or you can reach out to one of us later on. And that kind of leads me to this question here, which ties into the last slide. Should I be using Packers or some of those multi-level monitoring devices or liners you saw on the previous slide? Well, again, for some of the advantages and disadvantages we just talked about, that depends. So every site is going to be unique. A lot of those considerations are tied to time and money. But again, going back to what we talked about at the very outset, is when it comes down to the injection program at a site, at the end of the day, we need an open borehole, whether it has these tools in them or not. If they are in there, they need to be removed for injection and then be replaced. And that can be fairly simple to do for some of them. It can be very complex to do, very time consuming. But again, those are all decisions that if you're going to use those as part of your program, that have to be considered heading into the RDC process, because it affects how many boreholes you're going to drill on site. So the discrete sampling Bill mentioned, and also those liners and multi-level sampling ports we just talked about, all that provides a discrete sample at that interval. And we like to send those off to RPI's Project Support Laboratory in Golden, Colorado. They run the analysis for our clients pro bono. And we couple all this together, right? We have to bring together everything we've talked about in previous slides to come up with a plan for injection. So the rock core samples, the RPI lab data, geophysics, camera, et cetera. It all gets pulled together to come up with a picture and a path forward for us to decide where we're going to inject. Are there very specific zones? Do we have secondary porosities, extensive ones even, where we're going to have to walk the injection packer up and down the borehole? These are all considerations for design that we have to evaluate when we pull all this data together. So I'm going to hand it off to Bill here. He's going to show you a little how that pulls together for a real site.
Yeah, so we're going to try and be conscious of time here. I know we're getting close to the end of our time here for presenting, but I'll walk through this case study here. It's an ongoing remediation project that we're working on currently. It's located in South Central Tennessee, and it's a mixed-use residential commercial. Geology bedrock is going to be a Pennsylvania sandstone overlying limestone with a thin residuum of sandy clay on top of that bedrock material. Next slide, please. And just looking at a conceptual site model initially from the facility here, El-Napple site, benzene above the site-specific cleanup levels, which were specified at 887 ppb. Bedrock impacts were from roughly 11 feet to 27 feet below grade, and the varied concentrations of benzene within the two wells here of 2.29 to 5.94 ppm within groundwater. Next slide, please. So, as we talked about, coming in to fill the data gaps to try and get a better picture for the facility. Bedrock RDC consists of 3 Bedrock open borehole wells, 1, 2, and 3 installed to 36 feet below grade, and 3 additional wells installed 4, 5, and 6 to an approximate depth of 20 to 25 feet below grade. Next clip, please. Geophysical tools utilized out here included optical televiewer, caliper, and fluid temperature and conductivity. And going back through and talking about the aquifer characterization, utilizing the straddle packer for pumping tests and discrete interval sampling, while also looking at transducer data logging throughout the surrounding network. And looking at the cross-sectional conceptual model here, LNAPL and higher benzene concentrations showed themselves to be prevalent within the sandstone component overlying the limestone component directly below that, with a lower level concentration present. Next interval, please. And so just, again, coming back to this comment about the geophysics, looking at this particular slide versus the previous slide where we talked about the TCE site. And so kind of a similar parallel here that we want to highlight is, Derek can highlight with the pointer here that the OTB is identifying a fairly broken up zone down below, roughly from 22 feet to 23.5 feet, that would indicate a zone of higher K and groundwater transport just based on the geophysical logs. Caliper indicates this as well. But what we also want to note is that the geophysical contractor did identify some low angle bedding features directly above that could be contributors as well. And so again, coming into this idea of coming in with characterization and ultimately the remediation plan, we want to make sure that we're looking at every interval present. And with that tool, with that discrete interval sampling tool, we can actually isolate these individual bedding planes and that higher K zone and actually look at the chemistry and the fluid properties of that specific area within the formation itself. Next slide, please. And looking here at the NX cores, we talked about being able to identify features within the core itself. This is looking at a recent core from the site. And I want to call out here the top box is looking at 0 to 16 foot below grade. The lower intervals going from 16 foot to 25 feet, looking at the limestone unit and the contact between the sandstone and the limestone. But click ahead here is going to zoom in on that upper level box because, again, we're looking at this higher concentration zone in the groundwater present within the sandstone. And during drilling of this core and with the advancement of the open borehole and subsequent drilling, we noticed that there were distinct odors coming out from the air itself, which again is kind of a macro view of it when standing on the ground and reading chips. But when looking at the core itself, it may not be very easy to see here, but these highlighted intervals that we have within this core in front of us, there's visible staining and even a slight sheen on some of the rock features itself as you separate this core. And so when looking at these particular intervals, it's important for us to, again, scrutinize this and have this tool available to us when we come back in and actually investigate this borehole for the purpose of future characterization and ultimate remediation. So knowing this here shows us that there's definitely mass within this zone that needs to be addressed, and we need to be considerate of that when we come in with remediation. Next slide, please. So looking at some of the pumping test highlights, back one slide, please. So looking at the characterization highlights from the pumping test with the discrete interval, this is on a injection well 1, looking at adjacent monitoring well 1, which is located and screened specifically within the sandstone zone itself. And what we see here is not something that looks really all that impressive on the global scheme of the plot for the transducer within MW1, But we do see a little bit of a change here that requires a little bit of investigation with zooming in and kind of looking at this. So with a click forward, we can look at our other data from the time of performing actions on the site, and then see with a little more resolution and investigation here of looking at these individual changes with the plot. What we see here is actually that while in this particular case, monitoring well 1 did not particularly respond with the pumping test itself to a significant degree, but what it did show was that the water within MW1 behaved very similar to what you would see with a falling head test on a standard flood test. And so with Derek's pointer on the left-hand side here, looking at the orange kind of vertical tick, what we're seeing here, this initial rise in groundwater in this spot coincides with the insertion of a 300-pound packer into the borehole. The larger gray line directly adjacent to that is going to be the inflation of those packer elements and squeezing the water in that borehole to different places in the formation. So what you have here is a steep rise, or a relatively steeper rise in groundwater from actually inflating that packer element. And then that next orange line there is turning the pump on and evacuating water from that specific interval. The next one we see here again is inflating the packer at the next interval below that, and so on and so forth, and deflating the packer and draining the formation back into the lower interval itself. So we can see that there's a behavior here that we can monitor in the surrounding network to see how connection and reaction to actions on the other boreholes within the formation affect each other. Next slide, please. And then here is a little bit of a different characteristic, but something that's quite similar to a step-down pumping test that you would see in a more traditional sense. And so what we have here again is pumping from injection well number 2 and looking at the hydraulic head change in NW6 adjacent to it. And here what we see is pumping on a low volume basis for the purpose of purging and sampling, with the orange line on the far left. And then the smaller gray line, or the gray line directly adjacent to that, represents increasing the pump speed for the purpose of stressing the aquifer and looking at surrounding response in the adjacent monitoring wells being monitored with transducers. And we can see that process going down the plot here at respective intervals down the borehole. So the one he's pointing at right now is going to be your 22-foot interval. The next one below that is going to be your 23-foot, followed by 24 and a half and 26 and a half, looking at these specific intervals within the borehole moving down. Next slide, please. I believe that wraps us up for the characterization part of it. So again, just a little teaser for that particular characterization case study, leading into next week for a little bit more information on remediation related to that site and others.
Okay, and I apologize for that fragment on the screen, Bill. Your certification's there next to your name. We got a little hiccup there. Sorry about that. Got a couple questions here from the audience. I guess if it's okay with you, Bill, I'll moderate those and then jump in as necessary. So I guess asking of you, hang on a second, we'll go to the first one here. So first question is, the ideal 6-inch hole size, is that 6-inch borehole or 6-inch completion? I.e., could you elaborate on the construction with 6-inch casing?
Yeah, I can take that. The 6-inch completion we're talking about is specific to the open borehole and rock, so the actual drilled borehole. And as we've noted before, the well construction, or the specification that we need, are open boreholes for our particular purpose. So for the characterization, we want to be able to insert tools within that borehole, whether it be geophysical tools, downhole camera, or this packer assembly for the purpose of aquifer characterization and analytical testing. So these boreholes are going to have some sort of surface casing that's going to isolate the overburden contribution and protect that bedrock unit for the purpose of preventing any sort of cross-contamination, and then utilizing open boreholes for this purpose. So we're not talking about cased wells with a constructed filter pack here. We're talking about that specific open borehole remaining in place for adding tools later.
Sure. And I think you touched on, there's actually a couple questions here about cross-contamination within that water column. So I think you handled that one as well. Is there anything you'd like to add to that?
No, I think we're good. I think, yeah, the surface casing prevents from the overburden side, and then other tools can be utilized, like the liners or whatnot, if we're concerned about vertical contamination within the open borehole itself.
Yep. Another question here, and I know some people have to, if you have to leave, this will be available on the website. I know we're running a little bit long. This is a pretty intense topic, I know, but it will be available. For those that can stay, we'll stay and answer as many questions as we can. Got another one here for you, Bill. What is a heat pulse flow meter? I saw that included on one of your diagrams.
Yeah, it's a great question. Heat pulse flow meter is one of the additional tools that can be utilized in a downhole geophysical study. And essentially, what you can think of is that you're using a packer to isolate a specified interval within a borehole to see if there is any sort of fluid migration through that specific interval. So you're looking for some sort of sink or spring within that specific interval that you're isolating, indicating potential flow paths within the borehole and potential vertical migration within the borehole. So it gives you again another instance of where you may have contamination moving into and out of a specific location within a site.
Excellent. Another question here. What happens if you're pulling free phase product directly out of an interval that you're testing? What do you advise in that case? And I guess to add maybe a little bit to that, this is probably during the discrete sampling. Would you continue to sample that interval or that fracture, or would you shut that down?
I personally would continue to pull on it to remove mass from the system. Also, we can remove product from an interval and put that in a sampling container and utilize the LNAPL coming specifically, or the DNAPL in this case, from the site to actually calibrate the instrument at the laboratory for analyzing any sort of dissolved or sorbed phase that may be present specific to that contaminant at the facility itself.
Sure. All right. Question between a flow meter or a caliper, and which is the better tool to find permeable fractures? I guess I'll take that one since you've done a few here, Bill.
Yeah.
I mean, personally, it's best to look at a comprehensive suite, and a lot of geophysical contractors, whether it's us or you subcontract, it's someone you already have an MSA with or the client's comfortable with, we can work with either situation. It's really looking at that comprehensive suite, and most of the providers in that realm do that. Going back to some of the geophysical logs that we showed earlier, that's pretty standard these days. There was, actually, I have the ability to back it up here, I think. This example here that Bill used, some of them, I mean, the resolution on some of these tools these days, whether it's an optical or it's an actual tool like a caliper, you've got great detail, and to skip one of these tools really isn't going to save you a lot of time or money on site. You know, usually if you're trying to save costs on geophysics, and I don't recommend that personally because these suites are pretty comprehensive, we see clients or subcontractors try to cut out OTV or ATV, or maybe skipping heat pulse flow meter. It's not going to really save you a lot of money. It might save you a little time on site, but pulling all these together, and as Bill showed in a couple of his examples, each one shows you a different piece of the puzzle, and it can help you identify, or in some cases, significantly identify an area that would have been missed by other tools, you know, even multiple tools in that same hole. So I'm not saying, you know, again, every tool is a tool. We say that a lot, but it's true in this case. So a typical suite like this, most of the providers out there will run these tooling in concert with each other, and we can all sit down together and look at it to decide which zones make most sense for discrete sampling. Another question here about rock coring. You mentioned NX rock cores. Are any other sizes usable too?
Yes, you could use pretty much any size you want. And what we always advise, or what we stress when we do coring versus setting the characterization points, is that the core location is independent from the other characterization points. And what we found is from experience is that if doing a core location and then trying to essentially over drill or ream that core location out, even the best efforts of a very skilled drilling contractor can have some level of deflection from that original path. And what we've seen at times is that the core location can deflect, or the reaming bit can deflect, and essentially you have a cut in the sidewall of the borehole that prevents getting a suitable seal. And so for safe measure and for good best practice, we always recommend completing the core hole at an adjacent location, offset from your case open boreholes, just for ensuring that you have the best possible chance of having a nominal caliper size for that specific borehole that you're going to be going back into later.
And we've got a couple questions here about what type of borehole installs, between the coring, sonic, air rotary, and also, how you can use what we just talked about, this RDC process, to define the number of holes that we have to put in at a site. I'll handle a little bit of this, and then Bill certainly jump in here. Probably the first and foremost is Bill just talked about the different coring you can physically do. You can also take different sonic cores. I know some areas of the country that's preferential based upon geology, cost, and speed. As I mentioned in an earlier slide, in terms of putting in a borehole that I'm going to use for characterization and injection, again, personal preference is air rotary. Some areas where you're drilling in rock that's a bit softer, a bit less competent, blowing out that hole when you're finished is really important, trying to get a nice clean fascia on the inside of that boring. But even those best efforts can be thwarted in the field, whether it's over time or just degradation. Recently we did a site here in Pennsylvania where the borehole had only been installed about 6-8 weeks before we went out there. And because of some high angle interconnected fractures, there was significant just natural spalling on the inside of that borehole. So we definitely had to take into account that. It didn't preclude us from analyzing that zone, but that could be a consideration, is the aging in some of these softer, less competent materials. Once you move out of the transition zone, how well that works. In terms of eliminating the number of boreholes installed or minimizing that cost, it can be hard sometimes. The tools we showed you on the earlier slide, the West Bay, the Waterloo, the flute liners, the Solent systems, those can sometimes help with that. If those can be retracted from the borehole, that borehole can be used for injection, those can be reinstalled. So that gives you a borehole that wouldn't need a sister borehole adjacent to it for monitoring. They can be continuously reused. In other cases, doing the rock cores, doing the discrete sampling up front, you may break up your borehole installation into a couple phases. You may, say, put in 3, 4, 5 boreholes here, do an RDC, that's phase 1 of an RDC, analyze the data you've got back, decide, do I need to add some additional resolution in this part of the site, in this part of the plume? So breaking up the phases can help. But if at the outset, not to be completely concrete here, but if I can only put in, say, 5 boreholes, I'm probably looking at, some of those toolings we talked about, the multi-level port samplers, the liners. I'm probably looking how we can use those to mitigate the number of boreholes we need to put in, because those can be retracted and replaced, and they do give you various ways to monitor for NAPL or specific zones. But again, they have different costs associated with them. The liners tend to be a bit less expensive, but they're a little harder to move in and out because they have to be reeled up. The West Bay, the Waterloo, some of the Solent systems, that's a lot of pipe. Those are actual packers in some of those cases. So you've got to inflate those and seal off those zones. That can be tricky to handle. So you definitely need to use an installer who's certified by those companies, because that's a lot of management there. But they all couple up together. And that's why it's so important to communicate both AST to you, our client, other contractors throughout this whole process. You want to select tools that are complementary, that are cost effective, time savings, money savings, or break it up into phases like we just talked about. Sequence your events to be effective, both from a remedial standpoint and a cost standpoint. Is there anything you want to add to that, Bill?
No, I think you covered it quite well. Thank you.
Okay. Got two more questions here. How do you handle situations where the rock is too fractured, and are there concerns geophysics cannot be safely completed? And I'll add to that, there's a complementary question to that. When it comes to injection and you're putting your injection packers down hole, are there concerns with the tooling being jammed? I guess is the best way to break that one down. So significantly fractured rock concerns and tooling in and out of the hole. Over to you, Bill.
Yeah, I mean, if there's concerns about borehole integrity and significant potential expensive loss of hardware, we do have a drilling method that we just call it pre-drilling. And there's other presentations that can highlight this more in detail, or we could share it with the listeners offline, but essentially it involves pre-drilling the hole to the total depth of the remediation and backfilling that borehole with a bentonite seal from bottom of the hole to specified depth below grade. And then what we can do from there is go back in and trip in with direct push tooling and complete remediation as if it was an overburden type setting. And what we found that's really interesting and quite remarkable is that the injection tooling itself, or the injection methodology, cuts through the bentonite quite easily and can access those permeable zones within the formation that would otherwise be inaccessible, whether it be through traditional direct push due to early refusal, or off limits because the borehole integrity is too poor to be able to utilize packer assemblies like we've talked about here. Actually, we're utilizing this technique on a site currently this week down in South Central Tennessee, and doing a combination of overburden, straddle packer injection, and utilizing this pre-drill technique. So for the remediation side, it makes it this method works quite well. For the investigation, we would still have to be careful and considerate of this particular instance to make sure that we're still getting the data we need, but also not compromising hardware tools that we couldn't recover from a particular borehole in this instance. So if there's anything else you want to add to that, Derek?
No, I think that's good. And certainly, as Bill mentioned, in 2 weeks from today, the pre-drill webinar is going to be hosted again by RPI. Mike Mazzarese, our colleague, is going to be covering that topic in depth. So again, that tool is great for, as Bill mentioned, less comprehensive rock, transition zone weathered rock interfaces. We're running a little long on time here. I do apologize. I thank you for the number of you that have stayed. I've tried to pull together questions that are overlapping here. There are a few I don't think we have time to get to, but we will reach out individually to each of you if you asked a question that we didn't get to. There's a number of questions here about the tooling itself. Some of you have asked the biggest differences between ATV and OTV. Briefly, ATV is an ultrasonic acoustic image that's inferred, and the OTV is a physical image. It uses a CCD sensor, just like what's in your DSLR cameras. So that's a true actual photo downhole of the borehole. There's some other questions here about calipers and HPFM. So we'll reach out individually because that's a lot to digest here. And I know a number of you have been on with us for an hour. So I just wanted to say thank you all for your time. We'll again contact each of you individually if we didn't get to your question. And please join us next week for the corollary to this presentation, which is taking the RDC we just showed you and transferring that into an injection design for your site. Again, for myself and Bill, thank you very much for your time and hope to see you next week.
Thank you, everyone.